So, hello everybody. Today, our speaker is Professor Yukihiro Okamoto from Tokyo Metropolitan University. He shall speak on Legendrian non-isotopic is a conormal bundle in high dimension. So please.
Ah, Thank you for introduction, and I deeply appreciate organizers giving me this opportunity to talk. And in this talk, I will first introduce a question in contact topology and explain my main results regarding to this question. And next, I will explain a coproduct inspired by string topology, which appears in the statement of these results. And lastly, I will explain an outline of proof of results. So, let me begin with some terminology. So, let M be an odd dimensional to n-1 dimensional smooth manifold, and let alpha be a differential one form on M, and alpha is called a contact form on M if alpha wedge n-1 time wedge of d alpha, which is to n-1 form, and which is the same the same as the dimension of M, is nowhere vanishing. And in fact, we only consider the following example of contact manifolds, and which is a very basic example. So consider n-dimensional Euclidean space, and then we can associate its cotangent bundle, and it is identified with Rn cross Rn. And if we take Q1 data Qn as a coordinate, and let's take P1 data Pn be the coordinate of the fiber, then let's consider the sphere cotangent bundle of Rn. It is 2n-1 dimensional manifold. And, sorry. And on this sphere cotangent bundle, we can define one form as a pullback of this differential form on the cotangent bundle on the sphere cotangent bundle. And this is the summand of pi with dqi. And it is a contact form on the sphere cotangent bundle. Sorry. Next, let lambda be M is a contact manifold, and lambda be n-1 dimensional smooth submanifold. And such lambda is called a Legendrian submanifold of this contact manifold if the pullback of contact form on lambda vanishes identically. And in addition, given two Legendrian submanifolds, lambda 0 and lambda 1, we say that they are Legendrian isotopic if there is a smooth family of Legendrian submanifolds which connects lambda 0 and lambda 1. And in that case, I will write like this. And given a contact manifold, classifying Legendrian submanifolds up to Legendrian isotopy, which is equivalence relation, is an important problem in contact topology. So let me give an example of Legendrian submanifolds and introduce more specific question. So consider any compact smooth submanifold of Rn. Then we define lambda k which consists of QP in the sphere cotangent bundle such that Q lies in K and P is perpendicular to the tangent space of K at Q. And we can check that it is a Legendrian submanifold of this sphere cotangent bundle. And it is called the unit conormal bundle of submanifold K. And it is obvious from the construction that if two submanifolds K0 and K1 are smoothly isotopic in Rn, then the unit conormal bundle of K0 is Legendrian isotopic to the unit conormal bundle of K1. So it is natural to ask whether the opposite implication holds in general. And there are several preceding researches on this question. And a famous one is by Shende and Ekrom in Shende. The result is that consider two knots embedded circle in R3. Then if lambda k0 is Legendrian isotopic to lambda k1, then the knot k0 is isotopic to either k1 or the mirror knot of k1. And so the the answer to the question in the case where n equals 3 and 4 when k0 and k1 are knots, the answer to the question is mm, mm, yes, up to mirror. The answer to the question is yes. The tools they used is the following. Shende used so-called micro-local sheaf theory, and Ekron in Shende used so-called Legendrian contact homology. And in fact, the approach I will explain today is close to the second one. There, there are also results including high dimensions. So let's K0 and K1 be compact submanifolds of Rn. And if lambda K0 is Legendrian isotopic to lambda K1, then in the same paper, Shende proves that the group link of the fundamental group of the complements are isomorphic. It is also shown by Aspirant that the fundamental group of the based loop space of the complement are isomorphic. And here, any dimensional sphere is identified with compactification of Rn, and we regard K0 and K1 can be seen as a submanifold of sphere. And in addition, in fact, this isomorphism preserves the Pontryagin product induced by concatenation of base loop, or concatenation of loops at the base point. And I'd like to explain my results, new results, which includes I'd like to explain my results in new results in high dimensions. And it is recently published. So to state the result, first consider compact submanifold K of Rn, and consider the relative homology group of the pair of K cross K and its subset which this is diagonal subset with coefficients in F2, and we shift the degree by 2 minus codimension k, and let me abbreviate by HK. And in the next section, I will introduce a coproduct on this homology group, delta K. And the first result is as follows. So if lambda K0 is Legendrian aspect to lambda K1 in the sphere cotangent bundle, and each submanifold is connected and its codimension is greater than or equal to 4, then there is an isomorphism from HK0 to HK1, preserving the coproducts, which means this diagram commutes. And in fact, this condition is crucial, and I will explain the reason in the last section. And this is a result in a general case. And as an application, I obtained this second theorem. So consider integer d greater than or equal to 4, and consider any closed surface which is connected and not equal to the two sphere. Then there is two embeddings of this manifold, and d minus 1 sphere crosses the surface into R2d plus 1, which is codimension d, such that their images K0 and K1 satisfy the following properties. The first one is that these Legendrian submanifolds have the same so-called classical invariants. And these are Legendrian isotopy invariants, including so-called Thurston-Benningham number, and also includes isotopy class as a smooth submanifold, forgetting the contact structure. Second property is that the coproduct for K0 vanishes, but the coproduct for K1 does not vanish. So in particular, by the previous the first theorem, this implies that lambda K0 is not Legendrian isotopic to lambda K1. So in summary, these two Legendrian submanifolds cannot be distinguished by classical invariants, but they can be distinguished by using these coproducts. Is there any questions so far?
Please continue. Yeah.
Thank you. And in fact, this theorem, this surface appeared in this theorem can be generalized to more general manifolds. So next, let me explain how the coproduct is defined. So again, K is a compact submanifold of Rn, and we would like to construct a map delta K from the homology of this pair of spaces to the homology of the product, uh, the square of this pair of spaces. And, it is isomorphic to the twice tensor product of this homology group up to shift of degrees. And, and before explaining this definition, we should note that there is a natural identification as follows. So consider a path consider the space of paths in Rn, which is linear and whose endpoints are contained in K. So this path gamma is a linear path whose endpoints are in K. And since linear paths are determined by only their endpoints, so this space is naturally identified with K cross K by this map, which maps paths to gamma to the point gamma to gamma 0 and gamma 1. And by this identification, the diagonal subset corresponds to the set of constant paths in K. So let's replace this space by this square of K by this space of linear paths. This space of linear paths. And let me denote it by P linear K. And the idea of the coproduct delta K is can be explained as follows. So suppose that we have a family of paths, family of linear paths in P linear K, parameterized by some space or manifolds U. So we have a family of we have a family of linear paths gamma U. And for such family of paths, we can associate a family of pair of paths parameterized by U tilde, which consists of the pair of T and U, and T ranges from 0 to 1, but T is not equal to 0 and 1. And U is a point in this space such that gamma U of T is in K. So what does it mean? So sorry. Given such family of linear paths, so we can illustrate like this. So we have a family of linear paths. Then at some U, the path gamma U intersects K at interior point at T. So gamma U T is contained in K. Then for such gamma U, we can split this path at this point to get a pair of linear paths. So this is a pair of linear paths parameterized by this space. Mm. And this is an idea of construction. And, and following this idea, and we can define delta k from the homology group of this space identified with k cross k and diagonal. Um, and, and I think there are several ways to give a precise definition, give a rigorous definition of this delta k. And, one way to give a precise definition is to use the most homology on k cross k. So we, we did this homology group is isomorphic to the most homology of k cross k. And mm, but by using most homology and using most homology and using most theory on k cross k, one can define rigorously such operation of, I mean, I mean, given a homology class in P linear K by delta K maps homology class of here to some homology class of this. The square of P linear K. Um, sorry. And, instead of giving a precise definition, let me um, uh, let me explain one simplest example of computation. So let's consider the case where K is a hop link in R3, and it is a union of circle. It is a union of circle in a plane and another circle which links to it and which passes through 0, 0, 0. And consider a homology class represented by this family gamma theta. It is a path as in this picture. So the starting point of gamma theta is this point 100, and the starting point is fixed, but the ending point is this point, and as theta varies from 0 to pi, the end point um, moves along this circle. So we get a family of such linear paths. And for such homology C class, delta k of x is a homology class of degree 0, which is represented by the pair of paths as follows. So this family of paths intersects k if and only if theta is pi. And and we split this gamma pi at t equal 1 over 2 to get a pair of paths. So, and this represents this zeroth homology class. Um, and and let me explain the examples of some example of submanifolds appeared in the second theorem. So, um, as in as in the second as in this theorem, let t be an integer greater than or equal to 4, and let sigma be closed to surface, not equal to sphere. So first, the submanifold K0 is constructed as follows. Or, uh, as a first step, uh, let's embed this surface into RT plus 1. And so that this surface is contained in the unit sphere. And, and let me depict it by, I mean, by, I mean, reducing the dimensions. So let me depict this sigma by this bold line. And RT plus 1 is this line. And then the submanifold K0 is defined as a product of the unit sphere in RD and the sigma um, we embedded in RD plus 1. So we obtain a submanifold K0 in RD plus 1, R2D plus 1. So the picture of K0 is like this. This is sigma and this is ST minus 1. And the product, we take their products. And the another submanifold K1 is constructed as follows. So we take the plus 1 dimensional sphere, which link um, um, whose radius is sufficiently large, and which links to ST minus 1. And if its radius is sufficiently large, it is disjoint from K0. And we take a connected sum of K0 and this large sphere. Then we get another embedded submanifold K1 in R2D plus 1. But the at a smooth manifold, K1 is diffeomorphic to the original manifold K1. And because K1 is obtained by connected, K1 is obtained by connected sum of K0 and sphere. So, and the main result of the second theorem was that the coproduct for K0 vanishes, but the coproduct for K1 does not vanishes. So let me explain the reason. So let me explain why the coproduct for K0 vanishes. Um, this is because for any linear path whose endpoints are in K, for any such linear path, any such linear path does not intersect K0 at interior points. And the reason is as follows. So consider any path whose endpoints are in K0 and consider the projection in RD. Then this path is projected to a linear path whose endpoints in the sphere, but such path cannot intersect this sphere.
Mm.
So, so this means that this path before projection also cannot intersect K0. Sorry. I, uh, as long as these 2 points are not the same, as long as the endpoints are not the same, and, and even when the the gamma is a path which is projected to a single point, I mean, the path is contained in the fiber of this point. In such case, we can consider a projection to RT plus 1, and this path is projected to a path whose endpoints are in the surface C sigma. But again, since sigma is embedded in the unit sphere, so this path cannot intersect sigma at interior points. So and this again means that this path before projection does not intersect K0 at the interior point. And, and in fact, this implies that delta K0 maps every homology class to 0. And the second claim is that the 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 coproduct for K1 does not vanish. Since sigma is not the two sphere, so we can first take a non-vanishing cycle. I mean, representing a non-zero homology class of sigma. And C, let's take such cycle C. And there is an homology class X represented by a family of linear paths. It is parameterized by C cross st minus 1, st minus 1 cross C. And this gamma U is a linear path like this. And this C parameterizes the the starting point of gamma U, and st minus 1 cross C parameterize the ending point of gamma U. And for the same reason as in the case of hop link, And there, there is a case where gamma u intersects, sorry, there is a case where the gamma u intersects k0, sorry, intersects the k1 at the interior points. And in fact, we can compute that the, um, the homology class delta k1 of x does not vanish. Sorry. So far is the second section. And is there any questions so far?
It's so you can ask at the end of your talk here. So
Ah,
please
yeah,
continue. Yeah, thank you.
thank you. Okay. Um, okay. And in the last section, I'd like to outline of the proof of the first theorem. And for the proof, there are 2 points. I mean, the first point is that we use Legendrian ISP invariant, so-called strip Legendrian conduct homology of Legendrian submanifold.
So that's your definition, right?
I will explain later how it is constructed. Mm. And it is equipped with coproduct. And and these invariants are defined um, under so-called index positivity condition on Legendrian submanifold. And this condition is also explained later. And the second point is that when K is a compact and connected submanifold of Rn, whose codimension is greater than 4, then in fact the unit conormal bundle of K satisfies this index positivity condition. So this means that we can define the strip Legendary contact homology and coproduct for lambda K. And moreover, we can compute this invariant. That means there's an isomorphism from the strip Legendary contact homology of lambda K to the this homology, I mean the relative homology group of, of K cross K and the diagonal. There's an isomorphism from here to here, preserving the coproducts. This delta case is what I explained in the previous section. And assuming these two facts, the theorem one is proved as follows. So suppose that lambda k0 is Legendrian isotopic to lambda k1, and each k and k0 and k1 is connected, and their codimension is greater than y equal to 4. Then the Legendrian isotopy invariance of the strip Legendrian contact homology with coproduct means that this invariance for lambda k0 is isomorphic to this invariant for lambda k1. And by the second fact, this the strip Legendrian contact homology with coproduct for lambda k0 is isomorphic to this HK0 with coproduct, and similar for K1. So in summary, we obtain a isomorphism from here to here. Please recall their definition. There's isomorphism from here to here, preserving the coproduct. Okay, and I'd like to explain the first point, the first result and the second result, including how we can define the strip Legendrian contact homology. Okay. Okay. Let's take let lambda be a compact and connected Legendrian submanifold of the sphere cotangent bundle whose Maslov class vanishes. And in fact, the construction of them can be generalized to a more general contact manifold, which does not have with no contractible periodic level of its. But let me restrict to the case where the case of sphere cotangent bundle. And associated to this contact form, one can define a vector field, so-called Reeve vector field on this contact manifold. And in fact, in the present case, it is explicitly written by this. Okay, and let's consider as a set, a lambda, consisting of paths in the sphere cotangent bundle, such that it is tangent to the Reeve vector field, and its endpoints are contained in lambda. So it is a path like this. And such path is called a Reeve code of lambda. And for generic, after a generic perturbation of Legendrian submanifold, every Reeve code satisfies a condition so-called being non-degenerate. And we can define a integer for every Reeve code, mu c, and it is called a Maslov index of C. And let me explain sorry, let me explain next the notion of pseudo-harmonic strips. We take an almost complex structure on R cross the sphere cotangent bundle, satisfying several suitable conditions. And in particular, it is sorry, on this manifold, there is a natural action of R, which is translation on the R coordinate. And we require that J is invariant by this RR action. And then for any Reeve codes C0 and C1, we define so-called moduli space of pseudo-homologic strips, which consists of a map from R across the interval from 0 to 1 to this manifold, which satisfies this Cauchy-Riemann equation. Cauchy-Riemann equation. And the boundary of this strip is mapped to R cross lambda. And in addition, it satisfies an asymptotic condition as in this picture. So if the R coordinate goes to infinity, it converges to the wave code C0 at positive infinite end. And conversely, when the R coordinate goes to the negative infinity, it converges to a wave cause at the negative infinite end. And in fact, there's a natural action of R on the domain of U. And as I said, there's also an action of R on the target of U. And in fact, this set is preserved by these actions. So we model out this set by R cross R. And this is the definition of moduli space of pseudo-homologic strips. And in fact, after generic perturbation of lambda and j, this moduli space is a smooth manifold whose dimension is computed by the Maslov index of C0 minus Maslov class, Maslov index of C1 minus 1. So let's define a graded vector space, C lambda, which is freely generated by the set of wave codes. And the degree of wave code is given by Maslov index minus 1. And in addition, linear map Tj of degree minus 1 is defined as follows. Given any wave codes, it is mapped to summand over C1, whose degree is the degree of C0 minus 1. And the coefficient of C1 is given by modulo 2 count of this moduli space. Modulo 2 count of this set. In fact, from this condition, this is a zero-dimensional manifold. And moreover, we can prove that it is a compact. So it is a finite set. So we can count the number. We can count the cardinality of this set modulo 2. However, in general, the square of dj is not equal to 0. But there is the following fact. I mean, if this condition star holds, then the square of dj is equal to 0. And this is a condition what I called the index positive. which means that for any wave course which is homotopic to a constant path with endpoints in K, then for any such wave course, its Maslow index is greater than 1, uh, equivalent to the degree of C is positive. And so since the square of dj is equal to 0, we can define HL lambda to be the homology of this chain complex. And it is called the steeple-Legendrian contact homology. And why this condition is necessary? So let me try to explain the reason. So this is an index positivity condition. So this condition is necessary to prevent so-called bubble for pseudo-homologic strips in one-dimensional modular spaces. And without this condition, there can be a sequence of pseudo-homologic strips in this one-dimensional modular spaces, which converges to and which converges in a sense of so-called Gromov convergence to a homologic such pair of homologic curves. And intuitively, a small part of strip grows as n goes to infinity, and in the limit when n goes to infinity, this part goes to the negative infinite end. And the index positivity condition prevents such phenomenon. And sorry, and sorry. And if such bubble does not happen, then we can show the square of dj is equal to 0. And even when this index positivity condition does not hold, we can define a so-called Chekhov-Eliashvili differential graded algebra. But it involves not only pseudo-homologic strips, but more general pseudo-homologic curves with arbitrarily many legs. So, so it contains and it can be and the chain complex defined under the index positivity condition can be seen as a reduction of this DGA. So it contains much information than this, but as a payoff, it is much more difficult to compute in general. Anyway, okay. And we get a chain complex, and in a similar way, by using pseudo-homologic curves with two legs, we can define a map from this chain complex to twice tensor product of the chain complex. And again, with the index positivity condition, we can show that this delta J is a chain map. And it induces a coproduct delta lambda on the strip Legendrian contact homology. And we can show that it gives Legendrian isotopic invariance. That means that if lambda 0 and lambda 1 are compact and connected, Legendrian submanifold satisfying the index positivity condition. And if these are Legendrian isotopic, then there is an isomorphism between the strip Legendrian contact homologies, preserving the coproducts. So far is the first point about strip Legendrian contact homology and coproduct and its invariance under Legendrian isotopy. And in the remaining time, I'd like to explain the second part roughly. Sorry. So the second part is about the computation of the strip Legendrian contact homology for the unit conormal bundles. So let K be an compact and connected submanifold of Rn. And there's a way to compute the Maslov index of the Rave code of the lambda K, the unit conormal bundle. And we can prove that the Maslov index of the Rave code is bounded from below by the codimension of K minus 2. And in particular, if the codimension of K is greater than or equal to 4, then it is bounded from 2, bounded from below by 2. So lambda K satisfies the index positivity condition. And in particular, this means that the strip Legendrian contact homology with coproduct can be defined for lambda K when the codimension is when the codimension is greater than or equal to 4. And the key result in the second point is that there is an isomorphism from the strip Legendrian contact homology for lambda K to this homology group, which in turn defines the coproduct on this strip Legendrian contact homology, and another coproduct on this homology group. And in fact, the idea of the proof is essentially contained in the paper by Rachev and In. And in this paper, they computed the Legendrian, they observed the Chekanov-Eliashvili-Berg TGA of lambda K when K is not in R3. So, so I generalized some argument in their papers to high dimensional case. And we can prove this theorem. Let me explain a bit. Let me give several comments. So, how this isomorphism is constructed. So we have identified K cross K with the space of linear paths, but it is homotopy equivalent to the space of smooth paths, not necessarily linear. So it is homotopy equivalent to PK, the space of paths, not necessarily linear. And we consider a moduli space of pseudo-homomorphic curves in the cotangent band whose domain is half strip. And we consider we use this such moduli space. And from the boundary condition on this holomorphic curves, if we restrict U on this boundary component, in fact, this path is contained in PK, which means that the endpoints are contained in K. And so it is contained in the PK, and it is homotopy equivalent to PK. So by using such moduli space, we can connect this steep Legendrian contact homology constructed by pseudo-homomorphic curves to a homology group of path space. Sorry, and this is a rough exposition, but let me stop here and thank you for your attention.
So you finish your talk?
Yeah, I finished. Thank you.
Thank you very much, yeah, for a very beautiful reason and sophisticated construction. So you just mentioned that you use some reason from, can you put the previous slide? That, yeah, Chickenop, Eliasberg, DGA, but Chilibak, Ecom, Lachef, they didn't define this delta operation, right? So you define the
sorry, sorry, and they did not, how to say, yeah, such the coproduct does not
yeah,
appear their paper, but
yeah.
they gave the following the idea of construction I explained. They construct they gave gave they gave a chain level chain level definition. I mean, in the chain level of the singular chains,
Yeah.
delta k when in the case of knots, and they constructed what they called string homology for
So the
k.
similar.
Uh, uh, yeah, this construction
Yeah,
involves this
I see.
coproduct.
So that's the only enrich DGI algebra. So yes,
And yes,
yes,
and they prove that it is isomorphic to the homology of this DJ
yes,
in degree 0.
yes, yes. So yes, so that means that there may be more invariant of the Legendrian isotopy from the consider the Chickenop, Elashberg, DGA is the coproduct here.
Um, sorry, sorry.
So I mean
Chicken,
that you mentioned in the previous slide that's a very this DGA is a very complicated to compute. Therefore, you use strip Legendrian.
yes,
And but that means that this chicken dog Elashberg DGI is contain more invariant, right?
complete,
More
you
invariant
said more,
Legendrian
contains more information.
information, right? But harder to compute.
Uh, and but it's hard to compete. Yes, yeah.
Yeah.
Mm.
So you also mentioned at the beginning of your talk there another approach using how to say local microchip, right?
Yes, yes, by Shende.
Yeah. Micro local shift. Yes. So, do you think that there's some possible way to apply this theory to get the proof the reason you check presented?
Uh, you mean, sorry, you mean, can we apply micro-local shift theory
Yeah.
to,
Yes. Some.
okay, the micro-local shift theory is related to such coproduct. Not, uh, um, um, okay, sorry, I don't have
And
any idea to,
yeah.
to
Yeah. Because nowadays kind of also the theory of micro local shift theory is very popular and replay flow theory in many aspects, right?
mhm, mm, mm, but yeah, mm, sorry, at present, I don't
Yeah,
have a good idea.
yeah. I also don't know.
Mm.
I just curious. Yeah. So yes. So is there more questions? If there are no more questions, let us thank the speaker again. Yeah. So
Thank you very much.
yeah. Thank you very much.